So our last topic, is going to be the generative neural networks. So slightly different topic compared to the other things that we have seen so far. But this is a topic that is becoming more and more relevant in many engineering applications, from mechanical, material science, civil engineering, and a lot of different places. So we're going to introduce basically two things. One is called the generative adversarial networks, or GAN. And then the second part is going to be what's called the diffusion models, or generative diffusion models. So at this point, examples like this may not surprise you anymore, because we're living in the world of AI, right? So usually what I like to do is to present these images and then ask people to find the real people. There are four of them. The four fake, four real. Can you guess which one are real? They look all very realistic, right? Can you pick one that looks like a real person? So from the top, 1, 2, 3, 4, 5, 6, 7, 8. 7. 7 and 4. 2. Yeah, they're all fake. Sorry, I lied to you. They're all fake. Actually, there's a fun website called thispersondoesn'texist.com. If you go to that website, you can see the real-time fake imagery. There are literally millions of fake faces. So if you want to create some sort of an alter ego on Facebook or Instagram, you can go over there and take an image. And none of these exist, so so we're living in a world where AI is so precise and delicate in terms of what it can generate. So all these images that you saw is based on the method generated based on the method called the generative adversarial networks. So this one, I think a lot of you are already familiar with, but for those of you who are new to this area, generative adversarial network, or GAN, is comprised of two. One is called the generator, and then the other is called the discriminator. The generator network is the one that tries to generate fake imagery. So, it's this guy over here who's trying to fake. And then discriminator is kind of like a detective. Tries to, discriminate, fake images from real images. And that it is trained is a generator will artificially generate some image from some random seed inputs. And then either the generated image or the real image will be randomly presented to the discriminator. And then the goal of the discriminator, obviously, is to correctly discriminate the real images from, fake images. And at the beginning, obviously, cannot do a very good job, right? It's a randomly initialized neural network, and initially it'll generate some gibberish, looking images, and the job of the discriminator is going to be relatively easy. But in the meantime, the discriminator has never been trained either. So the discriminator is also, very bad in terms of its ability to discriminate the real images from fake images. So both are, equal at the beginning, and then after a few training, it becomes pretty obvious what the real image looked like compared to the fake imagery. So the discriminator is going to get better. But then, since the discriminator gets better, the generator will also try harder to beat that. And then eventually, the two networks will converge to what's called a Nash equilibrium, where this is kind of a game theory lingo. But that equilibrium is the point where the generator becomes so good at generative task that the discriminator is no longer able to discriminate the real versus fake. So the accuracy of the discriminator is going to converge to 50%, which is the coin toss, right? And then that is essentially the converged state of the generative adversarial network. So this is a typical example of what's called a Minimax game in the game theory. There are two different players in the game who have opposite objectives. One tries to maximize, the other tries to minimize. Maximize what? The discriminator wants to maximize the chance of correctly classifying real images from fake images, right? So the discriminator wants to maximize that chance. In the meantime, the generator's goal is to minimize the chance of discriminating the real versus fake, right? Because this guy wants to fool the discriminator. So it's called a Minimax game. And mathematically speaking, this is kind of the loss function that it tries to minimize. So let's kind of break this down into the individual terms. So we have the Minimax game, where the maximization happens with respect to theta d. Theta d is the parameter for the discriminator. Okay, so this is the one, discriminator is the one that tries to maximize this loss function. And then the generator, theta g, okay, is trying to minimize the same objective. Okay, now the objective has two terms. The first term, we have the expected log of d theta d of x, where x, okay, comes from the real data distribution. So p data is the distribution of the real images. So from a real image data set, you sample an image x is basically what this represents. And the capital D is the discriminator. So the discriminator wants to get the input from the real data, and then the discriminator is a binary classifier. So the discriminator will spit out either 1 or 0. 1 if it is real, 0 if it is not real, okay, fake. So for the data coming from the real image data set, we want to maximize the D, okay, or push the output as close as possible to 1 is what's happening in the first term. And for that same objective, obviously the generator wants to minimize it. So from the generator's perspective, we want the discriminator to make a mistake on the real data set, right? So in that case, the generator wants this to be minimized so that even for the real image, the discriminator start to say, oh, this looks fake, right? So that's the first term. The second term is pretty much the same, except that now the data comes from the fake image. So P of Z is a random seed, okay, a random number that the generator uses to generate an image. And from that random number Z, here, the capital G is the generator, and the generator will try to generate an image from a given random seed Z. That generated image will then be fed into the discriminator, which will then try to spit out either 1 or 0, right? The probability of being real. And from the discriminator's perspective, we want to maximize 1 minus that probability, okay? Because in case of the fake imagery, the right thing to do for the discriminator is to spit out a number that is close to 0, as small as possible. So 1 minus of that, we're trying to maximize from the discriminator's perspective. However, from the generator perspective, we want to fold the discriminator so that the fake image generated by the generator gets, fed into the discriminator, and then the discriminator gets fooled by the fake image and start to believe that it looks like real. And then in that case, the discriminator will spit out a number that is close to 1. And, because we're doing 1 minus of that, from the perspective of the generator, we're minimizing, right, that probability, right? So that is essentially the breakdown of what's called a GAN loss, GAN loss, which is defined as this equation over here. So, it's sort of a fun side story. Back in I believe 16 or 17, a group of artists in the UK, they actually generated a fake imagery using GAN, and then they actually submitted that to an art auction. And then, obviously people knew that it was a fake image, because back then the generative AI wasn't that good. But because of this artistic value, because they're the ones who first tried to generate an artwork using an AI algorithm, right? So considering that sort of a historical value plus, like artists, they also have this very complex philosophical thoughts. And with that value, I think that, particular artwork was auctioned at almost $500,000. And then, usually artists put a signature at the bottom of the artwork. So what the artist actually did was to write down this equation instead of the signature. So I thought that was, pretty cool. But this is the famous GAN loss, first introduced by a guy named Goodfellow. Ian Goodfellow is, back then was a graduate student. I believe Stanford. I forgot exactly where he was. And then as a graduate student, he had this crazy idea of 2 neural networks competing against each other. And then, this eventually became a thing and became so viral. Of course, training the Minimax game is not that simple, because think about it. We have one neural network trying to maximize something, and then the other network trying to minimize the exact same thing. And then they're kind of, fighting against each other. So training the neural network isn't terribly easy. So GAN, as a matter of fact, is notoriously difficult to train. So anyone who has an experience with GAN, they can share a really bad experience, because it's very hard to train. But there are several, very well tricks. The first thing is that, instead of solving the Minimax game problem all at once, very, common strategy is to just alternate between maximization and the minimization. So what that means is you train the discriminator first. And while you're training the discriminator, you free the weight of the generator, which means you're not updating the generator weights at all, right? And then after the discriminator is trained for a few steps, you then turn off the discriminator, okay? And freeze all the weights of the discriminator, and then turn back on the generator and train the generator alone. Okay, and then after a few steps of training the generator, then you go back to the discriminator, and then you basically repeat that process over and over again. Rigorously speaking, it's not the same as solving this Minimax problem all at once, but practically speaking, they will eventually converge to something that will be useful. And even if that solution is not exactly mathematically equivalent to this one, who cares, right? As long as you can generate a synthetic image, that's all we need. So that's one very common strategy. Now, the other very common strategy here is to consider the shape of the generated loss. So here we have a graph of log of 1 minus x. So the horizontal axis is the discriminator output. And then we have the graph of log 1 minus x, right? So this is basically what the graph shape looked like. Now, there's a problem with this graph shape, actually. And the problem happens when, at the beginning of the training stage. At the beginning, the discriminator is not very good at, doing things. Sorry, the generator is not very good at doing things. So whatever gets generated by the generator, okay, it'll be pretty easy for the discriminator to discriminate that, which means the output of D of G is going to be likely some small number. Okay. But why is that a problem? Well, I told you a couple of days ago, whenever I ask a question, there's a good chance that the answer is the gradient. Okay. So look at the slope of that graph. At the beginning of the training, when the generator is not that very good at its job, almost all the time, the prediction result is going to be near this range, where the slope is almost flat. And then when the generator gets better, if it ever reached that stage, then the output of the discriminator, because the generator's output is so realistic, will start to shift towards 1, right? But then over there, the slope is pretty steep. Okay. So it's kind of like, my favorite analogy is like teaching a student or, raising a kid. When you are not very good at something, your teacher barely gives you a feedback because the slope is almost flat, and that means there's almost no feedback going in to the student. So as a learner, your teacher doesn't tell you anything about how good or bad you are at doing certain tasks. Does that make sense? But then as you become better and better at your task, now all of a sudden everybody start to, point finger at you and say, oh, don't do this, don't do it this way, blah, blah, blah. I mean, that's kind of, a counterintuitive way of, developing someone's talent. Instead, what you would like to do is at the beginning, maybe you need more feedback, right? And then more hand holding. Like if you have a little kid, for example, you're going to need to tell the obvious things. Don't lick the scissor, or, don't climb up, a bookshelf. Like those things are very obvious, but they don't know, right? So you have to give feedbacks on those kind of obvious things. But then as the kid, grow older, the amount of the frequency of feedback, goes down, and you don't probably want to say too much about, obvious things, right? So that is more effective strategy of, training a kid or training a student. But looking at the graph shape of the generated loss, we're actually doing the opposite, right? So this, in fact, is one of the reasons why training this is so difficult, because at the beginning, we have a very small gradient, almost no feedback, hard to update. And then if it ever, does a good job, all of a sudden you have a very strong feedback, right? So the solution becomes very sensitive. The good news is that there's a very simple fix, which is to reformulate the loss to this one. So now we have the curve of negative of log x. And instead of minimizing this, we can consider maximizing this guy. And with that simple change, what happens now is when the generator is not so good at its task, we have strong feedback, big slope. And then as the generator improves its performance, now the slope is more flat and we're not giving too much of strong feedback. So putting this all together, this is kind of the usual pseudocode for the training of GANs. So we have the for loop, and then inside of the for loop, there are two parts. The first part is the update of the discriminator. And the gradient for the discriminator is based off of these two terms, the discriminator loss and the generator loss. And then we're actually maximizing this guy, okay? So we're doing the gradient ascent instead of descent, right? And update this guy. And then while the update happens on the discriminator, we do not change the generator weight. Now the second part of this for loop is the update of the generator. So now what happens is, the generator, loss term, we take the gradient. We don't really care too much about the discriminator because the discriminator loss is something that the generator cannot change, right? So the only thing that we can optimize is the generator loss. And then instead of the original 1 minus, this part, we're maximizing this. So maximization again. So, from minimax problem, now we have max problem. And then, while the generator gets updated, we freeze the discriminator weights and, do nothing about the discriminator. And then we basically switch back and forth, is how the GANs are trained. Now, on the specifics of different parts, usually what happens is we start from a random set of samples for the noise, so Z, and those random noise Z is what serves as a seed for the generator. So generator will generate some random image that correspond to some set of random numbers. And the Z is basically the parameter. And by changing the value of Z, you can change the output of the generator. And then during the training, we're just generating some random inputs to the generator. So that's the first set of samples. The second set of samples, we get it from the real data. So let's say you have a database of all kind of human faces, right? That could be your database. And then you randomly select a facial image, and that's the sample X. And then from those real samples and the noises, basically we evaluate the gradient. So again, the discriminator loss is defined on the real images, whereas the generator loss is defined on the generator generated images. So that's the random noises. For the training of the generator, we do not need the real images in this case, because again, the discriminator loss is something that the generator has no control of, right? So we skip that part, but simply just go directly to the random image generation, and then that's how we train them. So in theory, you just go back and forth between the two. And in theory, it's, the implementation itself is pretty easy. You just need to write a for loop. And then the loss function is pretty straightforward. So you can implement it with only a few lines of code. But the actual training, there's no guarantee that this is going to converge. And that's why GANs are notoriously difficult to train. You may have noticed that the first part of the training, the discriminator training part, there's some, for loop over here. So actually the discriminator gets updated multiple times, K steps. This is sort of a magic number. So depending on the authors, some argue that you just need K equals to 1. But some, other people argue that K needs to be higher. And there doesn't seem to be any consensus or any scientific proof or anything. So this is something that you have to experiment with. I think the bottom line is you don't want to update the discriminator too fast, because if the discriminator becomes too, I mean, gets better too fast, then the generator sort of lose the interest of learning. It is kind of like you have a very strict and very you have a very strict teacher who has a very high standard. You will never be able to impress this person. And as a student, you don't have any interest of learning anything, right? I mean, like when you're a kid, what your parents would do is to, just give you a compliment, even for the things that are not, terribly impressive. Like I have a little kid in my home, and I give her a compliment for, some really, bad drawings, to be honest, right? I mean, she's not drawing anything that's realistic or, has an artistic value. She would just draw something that, doesn't look like me at all, and then, give it as a present. And I just say, oh yeah, this is a great drawing. And that's kind of how you keep the kids motivated, right? And keep trying. Like you need that kind of compliment. Same thing for undergrad students. You cannot, always give them like really tough homeworks and, things like that. Then they'll just drop out of the course and, you know, not learn anything. I mean, you guys have that experience as a student, right? Some courses are just intimidating, right? Straight from the get-go. And for those courses, you don't feel any, interest of learning anything, which is why I put the neural operator to the later part of the course, right? Start with the easy one so that you can stay in the course. It's the same thing. You don't want to update the discriminator too fast, because in that case, discriminator is too good, and the generator will never get any compliment, any positive feedback, and the generator will just always get almost no feedback, right? No useful feedback. It's basically just keep saying to the generator that, oh, you're wrong, you're wrong, you're wrong, you're doing it wrong, right? Never get a compliment. So in that case, the generator, will not improve, and the training just stales. So you want to update the discriminator, by a very subtle amount, so that, by fluke, generator will fool the discriminator and then gets motivated, right? So that's kind of the, really hand waving. So I tend to prefer the small k, so that the discriminator gets updated much slower. But again, I guess it's sort of debatable. So here's kind of an example of training GAN on the handwritten digits. So here, the goal is to generate some fake handwritten digits, right? And then here we plot the loss of the generator, which is the orange curve. And then we have the discriminator loss, which is the blue curve. And then they're sort of fighting in, at the beginning. So it's very noisy, goes up and down, but then eventually sort of, converge somewhere. This is not the most excellent example, obviously, because this is a very simple set of images, and the generated images are not very impressive. But that's because, we use a very simple architecture. And as a matter of fact, this is the implementation of the generator and the discriminator in TensorFlow. So this is not PyTorch, but you should be able to kind of understand the structure of the code. So we have the linear layer. So in TensorFlow, it's called a dense layer, followed by leaky ReLU. And then we have batch normalization. So that's something we learned already. And then that is one block. And that block repeats 3 times. So dense leaky ReLU batch norm, dense leaky ReLU batch norm, dense leaky ReLU batch norm. 3 times, and then finally, you know, it generates an image as an output. And then the discriminator is even simpler. So we have dense layer, leaky relu, dense layer, leaky relu, and then the final output. And then the final output has a sigmoid activation, which means it'll spit out a number between 0 and 1. 1 meaning real, 0 meaning, fake. And that's really it. That's really the definition of the generator and the discriminator. For the training, this is essentially the implementation of what I already explained. So I'm not going to go too deep into this code itself, but what's really going on is, we generate some random noise, and then from the random noise, the generator generates the fake images, and then the two part of the for loop, right? Update the discriminator, update the generator, and we basically repeat this forever. Okay. Any questions so far? How am I doing on time? We'll have 25 minutes. Good. So here's one example of GAN applied to material science problem. So we have some material microstructure. There are lots of crystals, and in between the crystals there are voids and pores, right? And we would like to generate synthetic images of those microstructures. So this is a very typical thing to do in material science, right? Because in material science, obtaining those kind of specimen is something that is, real hard. I mean, most of the material scientists, what they would like to do is to, run some computational experiment on real microstructures. Let's say you're interested in the permeability of some porous media. So how much of water can flow, right, through those cracks and pores, right? If you were to rely on real images, then your bet is to, cut a material, put it on the, microscope, take an image, right? And then obtain one specimen. And on that specimen, you run the simulation, and then you obtain the porosity, permeability calculation. And then, you go again, take another cut, put it on the microscope, take the image, run the simulation on the image, right? But then, this cut and try experiments, you don't have a control over the morphology, right? So if, let's say, oh, I want to know what happens if this crystal grows a little bigger. But then from that cut and try experiment, you have no control over it. Whatever is given to you is going to be your specimen, right? Versus if you can use this kind of generative AI, you can actually have a better control over your specimen. So you can generate a synthetic digital twin of your microstructure with varying crystal size distributions, or varying aspect ratio of the crystals, varying orientation of the crystals, and so on and so forth. So that's kind of the value of introducing generative AI in engineering experiments. If you're a mechanical engineer, things like the topology optimization is where generative AI is being used a lot. So again, you're designing some structural elements, and then you want to find an optimal structure that gives the maximal strength with the smallest material consumption. Then what is going to be that geometric shape? And again, generative AI is something that can facilitate the process of generating those digital twins. I've seen a lot of CAD CAM applications where CAD models, CAD parts, generative AI learns to generate those 3D geometry, and then it'll spit out some random geometry that looks realistic according to certain distribution. So there are a lot of applications that you can think of. In this particular application, we have the material microstructure, and this one is a convolutional version of the generative adversarial network. So inside of the generator, we have a bunch of the up convolution, unconvolution thing. So this is actually pretty similar to the convolutional autoencoder, where generator is kind of like the decoder. And then the discriminator is kind of like encoder. And this convolutional neural network will try to classify what's going on. And with this convolutional formulation, the GAN loss is evaluated patch by patch. So we set a small window, okay, inside of this big image. And for each of this small window, we evaluate the GAN loss. Okay? So for each location, we're evaluating how realistic those, local pattern is. And as a whole, we judge the, how successful the generation was. And then finally, in this architecture, we have DL and DG. Sorry, the ZL and ZG. L stands for the local local noise, and then G stands for the global parameter. So ZG determines the global morphology of the microstructure, whereas ZL determines the local variation, the stochasticity locally. So for example, ZG will determine things like the porosity of the overall microstructure. But even for the microstructure with the same porosity, the individual details can vary. And those varying details are captured by the local stochasticity parameter ZL. So here's some examples of using microstructure GAN. Here are some real examples. And here are some generated examples. This TL method is some other neural network method that is not GAN. Okay, so this is before GAN. And at the bottom, we have the GAN generation result. We have some closed up images for a better comparison. As you can see, the bottom row is much more realistic, whereas the one in the middle, we have some artifacts. We have some kind of a grid pattern, whereas the bottom row is very, realistic compared to the closed up images. Note that we're not doing a regression problem. So we're not looking for this image to be exactly the same as this one. These are just randomly curated real images, and these are some randomly generated synthetic images. And we're not necessarily looking for the one-on-one match. Quantitatively speaking, the GAN-generated microstructures are very realistic. I'm not going to go into the nitty-gritty details, but in terms of the void diameter, aspect ratio, the orientation, the distribution of the synthetic images are actually very similar to the distribution in the real image. So this is kind of a typical way of measuring how good, quantifying how good the generative images are on top of this visual inspection. Now, this is where kind of a fun begins, where let's say we have a real microstructure that looks like this, and then a real microstructure that looks like that. And somehow you want to find in-between image, okay? So using GAN, what you can do is to first encode this guy into, the generative parameter Z, right? And then same thing, you encode this guy into some generative parameter Z as well. And let's call, that a Z0 and then Z1. And by interpolating Z1 and Z0, right, you can produce in-betweens. And as you can see from this, this visualization here, this sort of, we're morphing this synthetic microstructure into this one. So gradually it sort of changes, like this. Of course, out of those many Z's, right, there are Z components that correspond to the orientation of the crystals. There are Z components that correspond to the size of the crystals. And by tuning turning the knobs, what you can do is to generate images with particular orientation of the crystals, or generate the images with the variable size. So from left to right, you can see that, at the beginning it is kind of slanted, and then, so minus 45 degrees, and then, it is vertically standing now, and then plus 45 degrees in this direction, and then they're all kind of laid down horizontally, right? Control that, or you can also, control the size of the grains. So as you go to the right, you see that the grain size is much larger compared to the ones on the left. You can also kind of, place different microstructure morphology at different locations, and then kind of make a Z values kind of gradually varying from left to right. And then this GAN learns to kind of infill what's in between. So this is, one of the figures actually I showed yesterday, where, we're, varying the size of the microstructures and, microstructure orientation and things like that. And then, find the relationship between the varying microstructures and then the chemical reaction. So the kind of the holy grail of all this is kind of a design optimization framework where the GAN basically generates some, microstructures. And starting from there, we use things like Park or neural operator or, other kind of AI-based physics engine to make a prediction of the performance, what the system response is going to be. That sort of goes back and compared to against user specified design constraints, design performance, right? And then based off of this predicted performance and the desired performance, things like reinforcement learning, this is actually something that we haven't covered in this course, but like those they so that this AI agent will then suggest of this new design, and then we basically go over the loop. In between, we have like uncertainty quantification. I mean, this is something that we haven't covered again, of course, but this a separate topic that deserves at least several hours of discussion. But what this can do is part is most uncertain about, and then on direct numerical simulations, and so that as we go the loop becoming more and more accurate, right? And then as we go over the loop, we'll get closer to an optimal design, right? And then that will produce some final design candidate, which then gets sent over to manufacturing and then material testing, right? And then obviously the digitally designed microstructure and digitally predicted performance is not exactly the same. It is not going to be exactly the same as the experimentally measured values. So that discrepancy then goes back and then used to update AI models, and then there goes another inner loop, right? And in the inner loop, we again produce a design candidate digitally, and then the outer loop again try to optimize that through physical experiments and manufacturing. This is kind of the really the holy grail of how it's used in material science, obviously, but also we can replace many of these with some other specific design problems. So I don't know if you're interested in designing a humanoid robot, then the design can be generated by something like GAN, right? And then the predicted performance is going to be something else than material properties. But the kinematic linkage could be designed in that way, and then go over the see. So any sort of engineering design problems sort of fall into this the same framework. So that is kind of the direction that the whole field is moving towards, actually. Well, yes. Yeah. So thanks for this example. So, what I would do is to train GAN to generate bars. Basically, the can be like, and then the physics engine is find trajectories and things like that. So the gate generation can be done by